This presentation deals about the development of a new 38-year time series of daily global fractional snow cover products based on fusion of optical and passive microradiometer data. It's a joint venture between the Norwegian Computing Center and the Norwegian Meteorological Institute, and it's done as an option project within the Snow CCI project. The idea about a global snow cover product based on fusion of passive microradiometer data and optical data came was established more than 10 years ago. And first year version of it was developed within the CryoClim project, and it has been further improved in different projects. The idea is to use a fusion approach, combining the best of each sensor type to have the best possible estimate of a daily snow cover. So here we developed a binary product providing a snow cover at the 5 kilometer grid resolution for the southern hemisphere. So one important characteristic with this product is that it's having full spatial coverage each day with no emissions due to clouds and polar night. The objective of option project to Snow CCI is to transfer from the binary variable to a fractional snow cover variable to estimate the snow cover on a 1% level of precision. The fusion algorithm we have established includes 3 different components. The optical component using AVHR GAC data is based on a Bayesian model combining different features. So we estimate the probability for snow, for cloud, and for bare ground. And for the passive microwaves using SIMR data and SSMI and SSMI-S data, we use a similar approach, having a set of features with the most comprehensive set for the SSMI and SSMI-S sensors. For fusion, we have developed 2 models, one for optical and one for passive microradiometer data, and combine them into one fusion model, having 4 stage, simulating snow cover for full snow cover to snow-free ground, and some additional states as well. So we are here trying to take the best of both sensor types with a higher resolution and higher accuracy from the optical and the ability from a passive microwave to map during the polar night and not be affected by clouds. The fusion approach is based on the hidden Markov model framework. So this is a sound statistical based framework. It's based on training. So we are establishing by training the probability density distributions and the transition probabilities. And for this, we are using high accuracy optical data. And we use the Viterbi algorithm for estimating the most likely snow cover state per pixel per day. So we actually have one hidden Markov model per grid cell in the product. In addition, we estimate the uncertainty of a fractional snow cover on a pixel level using logistic regression. For validation of a binary product, we have used for well-established data set or point measurements from stations and transects, and calculated accuracy, here shown overall as overall accuracy per year using the GHCND data. And we have also shown accuracy on a monthly basis for 2004. And you will see that in the spring, the accuracy is typically highest when we have a contribution, good contribution from optical sensors. It's somewhat lower in the dark period. And we are typically obtaining an accuracy between 90 and 93% for most of the time period of this time series. This time lapse is showing how the daily snow cover product develops. It's showing that it's not affected by the polar night, it's not affected by the cloud cover, and it's giving consistent snow cover estimates for each day. In the Snow CCI work, we are transferring from these 4 states we are using for estimating the binary snow cover to fractional snow cover with 1% precision. But we can't introduce 100 different states into a hidden Markov model. It would be unstable doing that. So we bridge these 2 levels by introducing 10 states, estimating um, um, the snow cover at the 10% levels. Transferring from 10% to 1% levels, we have 2 alternatives. One using interpolation between hidden Markov model states, most likely, and the secondary most likely states. And as alternative 2, calculating a secondary Viterbi sequence and estimate a fractional snow cover between the primary and the secondary sequence. We don't know which one will be best, but we have so far implemented the 10% states, and we are testing these interpolation approaches. So the second alternative seems to be a little bit better currently, but we have not finally concluded. For the future, we are most likely to transfer to European sensors with SIMR for passive microwaves in the long term. It's unlikely that we will have an American passive microwave radiometer sensor for a period up to SIMR, so we will probably close the gap using AMSR2 and AMSR3 data. And we will also use this to facilitate experiments preparing for the SIMR algorithms. For optical, we like to transfer to Sentinel-3. So this is readily available. And hopefully this will be an activity coming after this fractional snow cover development. So in conclusion, we have developed a binary snow cover product covering the period 1982 until 2015. We are currently improving the algorithm to estimate fractional snow cover and will hopefully cover the period up to 2020. And for the future, we are preparing to use Sentinel-3 for optical and SIMR in the long term for passive microwave radiometer data. Thank you for your attention.